Hello, this paper is batch norm with entropic regularization turns deterministic autoencoders into generative models. Quite a mouthful, but the short story is that if you have batch norm, if you have entropic regularization, you can get samples from deterministic autoencoders. I'm Amur. This is my co-author, Abdullah, Rashwan, Pascal, Poupart. We're from the University of Waterloo and the Vector Institute. Let's begin. So, deterministic versus variational autoencoders. A deterministic autoencoder, there's a fixed code for every instance. Variational autoencoder, you sample a code from parameters. Generating images from deterministic autoencoders, generally speaking, you sample images from variational autoencoders, not deterministic ones. Deterministic ones are for things like denoising and so forth, but we're going to see how we can generate samples. We're going to go over some advances in the field. We're going to go over aggregate posterior alignment, how that works in batch norm, and we're going to go over what our results imply. A deterministic autoencoder. We've got an encoder network here, a decoder network here. There's a data instance, it goes to the encoder, becomes a code, you decode that back to get a reconstruction x hat. In a normal autoencoder, you just minimize the square loss between these two terms. In a regularized autoencoder, you minimize the square loss, plus you have a regularizer probably here. There's a L2 regularization, spectral regularization of the encoder and decoder, and so on. Variational autoencoder, here you've got a data instance, it passes to the encoder, it becomes some parameter, you generate a code CI based on sampling from that parameter, and then you decode it back to get x hat. Now, here you've got a mean square loss kind of thing with log p being Gaussian. So, it's going to come as a mean square loss kind of term. If you estimate the variance in x hat, it's not going to be exactly like the previous mean square loss before, but it's going to be similar. And there's k loss here with the parameters to an isotropic Gaussian. And if you lower the k loss enough, you're going to get to a situation where you can sample from the isotropic Gaussian and make your own CI and sample that way. And you have variations like the beta VAE, where you put a term beta here instead of 1. You have info VAE, where you have mutual information between CI and XI. Now, in general, GANs outperform VAEs now, and that's not good for a generative model. And why is that? So you blame the loss on things like the elbow, which is what the VAE objective is called, and also on other factors like posterior collapse when CI and XI have almost no information. So the same code or the same code distribution is roughly put out for every data instance. And this happens when the encoder and decoder are of great power. Power is a non-descriptive term, but let's just think of it as depth, channels, functional approximation capability, and so on. Fixes like the info VAE, as I said, they put a mutual information term between the CI and XI and keep the code informative. There's other problems that's been pointed out, like lagging decoders and encoders in the training process, and we're not going to go into that. We're just going to give you a survey that there's issues with the VAE formulation. What are some solutions? Well, we can try deterministic autoencoder. We can have a regularized autoencoder, as we discussed, where you have mean square loss and a regularizer. You can have an optimal transport loss, which is the Wasserstein autoencoder, and the Wasserstein part deals with optimal transport. And you can tune the aggregate posterior. We can try a two-stage VAE, where you have a VAE on the latent space of a VAE. These are all some architectural variants. Now, in aggregate posterior techniques, you take each instance to a fixed code, and you try to align the code so that the overall posterior looks like a Gaussian. And in a VAE, you want to make the posterior for each instance code look like a Gaussian, and that's not as good as try to work with the aggregate posterior usually. So in our method, we call it the entropic autoencoder, the EAE, and we are going to use two things. One, if you have a batch norm layer and if it's converging, the mean index-wise is going to 0, the variance index-wise is going to 1. The maximum entropy distribution is going to be a Gaussian if you have a random variable with those constraints. And so ZI is going to obey these moment constraints. It's coming after a batch norm layer. There's no affine shift. So this is exactly coming without the usual affine shift that you put after a batch norm layer. You train by minimizing the weight sum of the square loss, and you raise the entropy. And you put some term lambda over here. So that's regularizer. We're not going to go into how to tune that right now. How does this work? So let's say we're learning a distribution Q to maximize the likelihood on some distribution P. And the objective is to maximize like this. And if you have P as a Gaussian, then this is obvious. If Q is batch norm, then these two terms are not going to vary, right? Because if the modes are converged, these are ideally constant. So you can't optimize this. This is a constant. But let's rewrite this a bit. We have here a KL term. We have here entropic term. You want to lower the KL, and you want to raise the entropy. And you can do that because this is a constant. So if you raise the entropy, you're lowering the KL. So we just need to put an appropriate entropic regularizer. And what will we put? Well, we're going to put the conjunctival link estimator. Now, this is a pretty old estimator, and it works by trying to find the nearest data point for each data point, basically. So for each data point, you find the nearest one, and you take the distance, and you just put it in here. These are constants. So in the process of optimization, you actually don't need to compute these. So that's a huge plus. The whole thing runs pretty fast in PyTorch, and I'll just go into a brief detour here and more point out that the conjunctival link estimator for entropy is used to make the Kraskov estimator for mutual information, and the Kraskov estimator has been used in the information bottleneck experiment. So there's some justification that you can make for choosing this over any other. Anyway, moving on to Salabé samples, we've got faces here, and these are C4 samples, and they're sort of tiny, but that's C4 for you. Now we have FID scores over here. And as I mentioned the regularized autoencoders earlier, the main problem with that is if you regularize light in space, you still don't know what it's going to look like. So you have to fit something like a multivariate Gaussian, like a Gaussian mixture model. And in those cases, our performances are pretty close. But when it comes to an isotropic sampling state, regularized autoencoders can't guarantee that. And we have a pretty big performance gap, though this could be due to lack of strong competitors. And we'll probably have to relook this a little bit, but yeah, we have a good advantage in isotropic sampling versus regularized autoencoders. That's the key thing. So let's talk about two things that I also want to mention. If you have a layer that's of a low dimension, you narrow it, so to speak, by lowering the dimension on either side, before it and after it, you put deep networks, and you increase the width, you increase the number of convolutional channels, you basically increase the functional complexity, then you often end up not needing the regularizer, which is really interesting. You just have to minimize the square loss, and you get a distribution in the latent space that is very close to a Gaussian, and the samples look pretty decent. And we've got more of these in the paper if you want to look at that. Now, what are possible extensions? This depth and narrow batch norm phenomenon, this is probably going to occur in classifier network as well. And so we can look at that. And we can look at whether such situations that are going to be well modeled by a Gaussian. And that's an open question. And we can look at different normalizations, and they're going to have corresponding Gibbs distributions. The Gibbs distribution is what we call a maximum error distribution given some constraints. And the Gaussian is the one for the second moment constraint. But if you have the L1 moment constraint, it's going to be to the plus. So that's another open question. So yeah, that's a summary of our paper. Thank you.